Okay, so now we know that if you look at this here, I've shown you that obviously the distance between the tube and the source is d, but remember we were measuring from the front of the source, so we've discounted, the distance that we measured d is slightly less than it should be by a certain amount x, because the source is contained within the container and not at the front of the container. So we know that this value x is now 2 centimeters. I've shown you that and how to calculate that. Now what I want to talk about is what effect does this have on our results for our graph. So our graph that we plotted was lnc against lnd, so we know that, okay, and we've got a graph that looks like that. The question is now, if you plot a graph of lnc against lnd plus x, so we've now corrected our distance and added on that extra 2 centimeters that should be added on, what effect does that have on our graph? Well, you can see we've done some analysis here, okay. What we've done is we've added on 2 centimeters to each of the values of d, so these are now the corrected distances between the source and the detector. And then what I've done is I've worked out what the fractional increase is. Now, because this is a smaller value, we're adding on 2 centimeters to every one of these distance values. Because this is a smaller distance here, by adding on 2 centimeters, we're increasing this distance here. The fractional increase in distance here is 1.1, okay? The fractional increase, or perhaps we could say the proportion that it's increased by is 1.1, okay? The increase in distance here is only 1.03, okay? So this has gone up by a much smaller amount, okay? It's gone up by a much smaller amount in terms of the proportion, okay? So the proportional or fractional increase decreases as the distance from the source increases, because that extra 2 centimeters is a smaller proportion of the overall distance. And that means that the extra 2 centimeters doesn't have the same effect on each of the ln values. When you take your lnd without x, that's what you get. When you take your lnd plus x, you get these values. And what you can see is, for the smaller values of distance, the natural log value has increased by a greater amount than for larger amounts of distance. The natural log value only goes up by a smaller amount for these higher distances here, and a lower amount for these smaller distances here. And there's a reason for that. The way that natural logs work, or the way that any log works, is as follows. When you've got if you take ln2 for example, that's going to give you 0.693. If you then work out ln4, that will give you 1.386, and that is an increase of 0.693. Okay, if you do 1.386 take away 0.693, essentially you get 0.693. Okay, so when you double your value, it increases by 0.693. Now, if you do this again with different values, because that might just be for 2 and 4, well, let's have a look. Let's do ln3 and ln6. If you do ln3, take your calculator, you're going to get ln3 is going to be equal to 1.099. Okay, and ln6 is 1.792. Okay, now if you do 1.792, take away 1.099, what you're going to get there, 0.693. Okay, when you double a value, the natural log goes up by the same amount each time. Okay, now when you, let's say that we've got a value like this now, ln5, okay, and ln 7.5. Okay, if you natural log 5, you get 1.609. If you natural log 7.5, you get 2.015. If you work out the difference between those, 2.015 take away 1.609, what you're going to get there is 0.406. Okay. Now if you take another two values, ln, let's say ln 16 and ln 24, okay, what you're going to get then is ln 16 will be 2.773 and ln 24 will be 3.178, and if you take those values away from each other, you're going to get 0.405. Now what we're saying here is then this has gone up by a factor of 1.5, okay, so we're multiplying this is equal to 5 times 1.5, okay, 7.5 is 24 is equal to 16 times 1.5. So what we're doing here is we're working out the natural log of a value that is 1.5 times greater than the original value. And whenever you take the natural log of a value that's gone up by a factor of 1.5, it increases by 0.405. Now the reason this one isn't 5 is just because of a rounding error. Because we've rounded these up, that comes out as 406, but it should be 405. Whenever you increase a value, whenever you multiply a value by 1.5, the natural log goes up by 0.405. And you can work that out because ln 2 is 0.693. Okay, so whenever you double a value, because we're obviously doubling these here, then the natural log increases by 0.693. Whenever you increase a value by a factor of 1.5, the natural log increases by 0.405 because ln of 1.5 is 0.405. Okay? Now you can see here that this has gone up by a factor, so this value here has gone up by a factor of 1.1. If you take the natural log of 1.1, you get 0.95, which is this, okay? This has gone up by a factor of, it's 3 recurring, isn't it? So 1.033 recurring. So whenever something goes up by 1.033 recurring, you're going to get, natural log of that is 0.33, okay? Which is that. So what we're saying here is because these have gone up by different factors, increased by different factors, okay, then it's had a different effect on the natural log values. So for a smaller value of distance, the natural log value goes up more than for larger values of distance. And what that means then is all of these LNC values are going to be the same, okay? So all the LNC values are going to be the same, but the LND values are going to move that way. They're going to increase. But for lower values of D, they're going to increase more. And what that means is it tends to skew your graph, so that your graph is going to get steeper because these go up more, these move to the right more than these values. So because these move to the right more, it tends to skew the graph like that. Okay? And that means you're going to get a greater gradient and intercept. Okay? And there we go.